Hello, hello. Sorry for the long starting soon. I am 3D printing parts for the tests today, and I had an accident with the 3D printer. But it should be alright now, I hope. I restarted the print so that we can get the parts in time, like in an hour or so. But it was quite unfortunate. That's what I got. Like, I have no idea what happened, but things happened for whatever reason. Anyway. So, today we do two things, mostly, maybe a bit more than two, depending on how it goes. As always, the first thing is that I implemented a basic SVM on stream, so space vector modulation, which means that now we should be able to have more voltage on our bus, which means we can get higher speeds and higher currents at the same speed or at the same voltage rather from the power supply, if we need to. And it also means that our dynamic of our motor controller will be better. We will have more voltage to work with, which means our controller has to become faster. We will not do any controller changes for parameters today because it requires us to do the modeling in MATLAB or something similar. And this is not what we will do today because it can be quite painful, quite time consuming and stuff. Today we will just test SVM. We will clean it up a bit and then we will do gravity compensation. And what is gravity compensation, you may ask? Gravity compensation is when we have a load. Let me show you what I prepared for today. So I have calibration weights that are like 100 grams and 200 grams and stuff. And gravity compensation is, I also have a crank that we will put on the motor and the container. And I print a container for another size. So we attach it to the crank and the distance to the center of mass is exactly 200 millimeters for us to be able to calculate moment of inertia if we want to do it manually. And we just load our weight here, close the lid, and we get a mass on the crank. And the gravity compensation algorithm provides us with what? It provides us with an ability for this mass to be fully compensated, so that no matter what angle it is on, it felt when I move it by hand as if it is not here, like as if there is no mass. And this is useful in many ways, especially if we talk about designing like robotic arms and such. So this is kind of advanced stuff when it's done for robotic arms, but given that we only have 1 degree of freedom, one motor, and we only have this weight, it will be easier to do. And that's what we'll do today. We will design a way to use gravity compensation, and we also will design an automatic way to verify the weight, like not the weight rather, but the moment of inertia of our load automatically, so that gravity compensation is assigned without us hard-coding the values. So if we do a good job, which I hope we will, by the end of today, we will both make sure that our SVM works correctly and that we have a gravity compensation done properly. But for now, let's start with SVM. I came somewhat prepared. I decided not to implement it on stream because it usually comes with huge amount of errors. I decided to implement it off stream, do the basic tests, and now that I know that the very basic tests are working, we can do other tests and make sure that everything works as intended before going to the gravity compensation. So let's do it. Let me turn on the power supply and motor. So the main idea here with SVM, what shall we see when we compare SVM to no SVM? Because we have two types of modulation now, given that we implement SVM, and the first one is pure sinusoidal modulation, and the second one is SVM. And the difference between them is that with SVM, we literally have 15% more voltage line to line. And this, in turn, in the motor control, has to provide us with 15% more maximum speed. So how do we achieve maximum speed on our PMSM motor? We just run it in the current loop, and we provide current task that is higher than the current that the motor will have in the steady state with motor spinning at max speed. So this is exactly what we will do. We will just set the current task to high enough value at a particular voltage, and we will just make it run, and we will just measure this speed using our encoder, and we will verify that it's higher when we use SVM compared to when we not use SVM. So let's do it. First, I have 24 volts on my power supply. This will stay constant for this test. And now let's go and actually remove the SVM first, because I was testing with SVM before the stream. And let's first remove it so that we can see our baseline speed, and then we will measure the speed with SVM. So our baseline will require us to remove this, and now we can flash so that we can measure the value. Okay, we are here. So we will see our value inside of our device that I think is not seen because of the way my camera is done. Let me make the motor smaller and the text smaller so that it's better seen. I cannot make this bigger, unfortunately, in Cube, so you will have to trust me on this. So we have our encoder M, and this will contain our speed value. And we are currently set up to run in the current controller mode. So we just provide task, current task, and this current task will force the motor to just accelerate until it can't no more, until it reaches the maximum speed on this voltage. So this is exactly what will happen. I will turn it on. The motor will calibrate itself as always, because we currently haven't implemented the parameter storage and calibration storage in the memory yet. And now it spins with the maximum speed. It can spin at this voltage. So it's still 24. And now we can see here, it is roughly 43 to 44, 42, so 43 on average. This is our speed, maximum speed that the motor can reach with our 24 volts supply. So now, without changing anything else at all, actually I can stop it still, so to prove that it works. This is a current controller, so it fights me, but it fights me with limited speed. Not speed, but limited force, and the force is limited by the current task. And the current task we have set is 100 milliamps. So we can also interpret this as a force task, given that we know the force constant. But let's make it spin. And now, the only thing we will change, we will not change the power supply voltage, we will not change anything, we will just change the way the voltage is modulated. And we will do it with a single define for now, because it's designed to work like this. For now, it's not the nicest design it can be. I will need to redo this slightly, but this is the design we currently have. So we just flash it again. And what we will see is that our speed will be actually higher. Or at least this is how it's supposed to work. And if it doesn't work like this, we are in trouble. So we come here, we refresh, let's open our encoder right away. Let's start it to make the motor calibrate itself. Let's open our encoder and let's see what the speed will be with SVM included, or rather started. And as we can see, it's roughly between 50 and 51, sometimes it's 49. So our average speed is roughly 51. And it has to be roughly 15% of what it was, 15% higher. So let's just test it. Was scientific. So we have, let's say 51, and we will divide it by 43.5. And this is 17%. Given that the values are jumping on and off and we don't know actual averages, because we don't measure actual averages, like this is close enough. So we should assume that it works. We have roughly 15% more of maximum speed with like no changes in hardware, no changes in power supply voltage, like it's still 24 volts, no changes in nothing, just because we changed the way we modulate the voltage. And now I can also see that it's still a current controller. I can stop it and it still fights me, and it fights me with the same current. Like modulation approach doesn't change the force that current controller currently fight me with, because it is unrelated parameter, unrelated feature. So I can still fight this really easily because it's still 400 milliamps. So let me release it. And now what we need to do to make sure that it works as intended, we need to do the same tests on different voltages to make sure that the behavior is consistent. And then we will also need to test how it behaves on different currents when we load it differently. So let's do the voltages first, because it's the easiest one. We will just change the voltage expectation, and we will just measure the speed again. So let's do it. We go... Oh my god, I need to close a few files. Let's actually close everything for now, and let's open only our main and our definitions. So let's remove this, and let me turn down the voltage. Actually, we may only need to refresh once, because we can literally change the voltage here. But to do this, actually, let's apply one change and refresh once. And the change will be that we expect 48 volts, so that we never hit our brake resistor, because it's important to not introduce any noise, because we don't have, as you can see, we don't have brake resistor attached. So let's do it. And how do we do this? We do it in the device. So here, let's set our expectation as 48, and this expectation only used for brake resistor control, because currently we now measure the actual voltage on the bus and drive a motor based on that. And that is why I can flash it once and just change my power supply voltage and see the difference in real time. So let's flash it. We currently flash it without SVM, so we will measure 4 points of speed without SVM. And then we will do the same with SVM, and then we will compare that they are roughly 15% apart. So let's do this. Let me change my voltage down to 12 volts. One moment. So my voltage is down to 12. Yep. And let's run. First, the model will calibrate itself, of course. And now it spins, and it spins slowly because voltage is low, and the speed of any motor is proportional to the voltage that is applied to it and the motor parameters. But for the same motor, the higher the voltage, the higher the speed. Now, let's go to our device and encoder, and let's see the speed. So we are roughly at 21. So let's note it as our test data. Let's say here. 21 at 12 volts. Now I can simply change the voltage on my power supply, and the speed will just increase automatically. So I increase the voltage, speed increases. And now we can go here and see that our speed is roughly 43. So let's notice roughly 43. Let's put a roughly sign at 24 volts. And it will be radians per second, of course, because this is what we use. We use CI units so that we have no problems designing control systems. Now let's increase the voltage to 36. Speed increased again. Now it's very fast. And let's see, our speed is roughly 66. So roughly 66 radians per second at 36 volts. And now we hit the limit of our encoder troubles. So we will probably have noise issues for a short period of time, but it should be fine enough, I hope. Let's see. If we will have troubles with 48 volts, we will not use it as a point. So let me increase the voltage to 48. Yes, we do have issues. We do have encoder issues, so let's not use 48 volts because new encoders that we designed like a week ago haven't arrived yet, so we cannot apply them, we cannot measure it safely, we cannot safely work with 48 volts because we have too much noise, because we haven't done a good job protecting the line, the data line in the previous design. Now, then let's use only 3 points, and we need to then, and this will be our sine modulation, and this will be then into the SVM modulation. So, and something, let's copy this, and let's actually with, so that we are sure about what we are doing. And here, let's copy this and put like that with SVM. Copy this 3 times, and we just need to fill in the data. So let's do it. Let's enable our space vector modulation and let's test it again. Enabled, let's flash. We are flashed, so let's run. The model will calibrate itself first, of course. And let's open, in the meantime, our device structure, our encoder, so that we can see the speed. So we currently have 36 volts, and let's see what the speed will be after we, oh, I forgot to enable it. My bad. Here, let's see. The motor is calibrating, and now it's spinning, and it's spinning roughly 76. So let's note it. Let's note it here. So we have roughly 76 here. So let me lower the voltage to 24. At 24 volts, we have roughly 50.5, let's say. And let's lower the voltage again to 12. And at 12, we have roughly 24, 25. So let's say 24.5. Nilbo, it's university exam time. I came yesterday, wasn't in chat. Python testing, was it? Yes, it was. But not testing. We were developing debug protocol in Python yesterday. Actually, that was quite a journey. I thought I will do it in one stream because I just decided I would like to change the way stream buffers, like streams, debug streams work in my debug protocol. But then I started thinking about it, and then I decided to change the way debug buffers work. And then I decided to change how Python wrapper work. And then I decided to change how write and read requests work. So it turned out to be like 95% of redesign for the debug protocol, and we were doing it for 3 streams. And actually, yesterday, I'd say we only like 50% done. But I would imagine people are tired of watching me developing the debug protocol because, like, I would imagine not many understand what I'm doing, even though what I'm doing is quite advanced and probably interesting stuff for those who need it. But for people who don't need it, like for practical reasons, it's probably boring. So now we are working with more exciting stuff, the stuff that can be seen, which is SVM and gravity compensation. Gravity compensation will be very visible, very like physical, so people will be able to see it and understand it when it works, and it should be nice. So, but after today's stream, we will go back to developing debug protocol, I would imagine, because like it's very important, at least for me personally. But today we are doing the fun, more fun stuff. So let's check the numbers. How are you doing actually? University exam times, but now it's April. Do you have exams in April? like in May. What year are you on? You said you were last year, I would, if I remember correctly, last year student, right? Tell me more. Let's compare. So we already compared these numbers. Let's compare our 12 volts values, which are 24.5 divided by 21 roughly. So it's roughly 16%. So within our measurement limit, measurement error rather limit. And let's test for 36 volts. It's 76. Divided by 66, it's 15% as well. So it's more closer to this, but also these numbers are not very precise because we are not averaging them. So as we can see, we did the basic test. We now know that SVM works. Let's go to 24 volts as our baseline for today, because it will be a nicest voltage to work with, because we know for sure that our encoder works without errors, and we can safely try to push like 2 amps of current through our motor to provide enough torque for us to actually work with a gravity compensation. So now, this is done, the first thing for today. Let me actually move the camera. Let me note that we are done here. Yeah, have exams in May, actually, April end, currently 3rd year out of 4. 3rd year is last semester exam. Tomorrow is exam, now resting time. I see. And what is the exam? What is the subject? I'm quite curious what you study. If other people also have exams, tell me what you study as well. I'm very interesting. And are you prepared to pass it successfully, or are you trying to cheat? Don't cheat, don't cheat, don't tell me you're trying to cheat. I will be disappointed. Not that you care, but still. Okay. So let's note that we are done with SVM testing, with the basic SVM testing, but this is good enough. We will still be testing SVM because we will be using SVM for our gravity compensation. So SVM will still continue to be tested later. It's computer graphics and image processing prepared enough to pass. I see, I see. Good luck then. Though I don't know how other people in chat, but I personally hate when people say good luck, because like the phrase I love a lot is as following: luck favors the prepared mind. I love this phrase, like this phrase a lot. And if people need explainer of what it means, it basically means that you will succeed. Like there is a higher possibility of your success or you getting lucky the more you are prepared. The better you study, the more you do, the harder you work. And it worked for me so many times in life. So luck favors the prepared mind, and I hope you are prepared enough. So, pointing out that we are done here. One moment. I'm lost. Oh, I know why I'm lost. One moment. Now I'm unlost. And I'm looking for an emoji. Oh my god, I need to put it in an easier to access place. Now, let's get to work with our SVM. First of all, we will start our testing with 100 grams here and some load on our crank. So let's actually assemble this. This was designed in Fusion. I don't think I have a good enough light to show it. Like this is the design. We have screws here, mechanism to assemble here. I probably better just showing the 3D model in Fusion. So it looks roughly like this. Our test setup, and we put a weight here, the weight that we know, so that we can test our gravity compensation. But first, let's assemble it. Let's first assemble it. A few screws, of course. Also, we need to screw it sideways, but I think I can just put the screw in and it's tight enough to not need a nut. At least I hope it will not fly into my face when we start testing. This would be quite unfortunate. So, but at least if it will happen, people will have a good laugh about it. Like this. Don't screw it all the way, always. A nice way to do it. Lightly at all of them first. And then finish them one by one. Okay, you are not... You don't want to screw in? Brother. Now it's going, okay. Okay, I think I designed tolerances a bit not well enough. Okay, so this one is done. Oops. This one is done. This one is done, and this one. And this one is annoying. Okay, let's use more leverage. Oh my god. Okay, actually, I need heavy oh my god. How to like say the word artillery? I need a screwdriver. Okay, that was awkward. And now where are my bits? My bits are here. Let's see, this one probably is the one. Yes. You are going down. Artillery is like... You don't know what artillery means? Like... These are big guns that send shells on far distances. And they hit heavy because they blow up heavily, and when you say you need to bring heavy artillery, it means that you need to do something like dramatic, something high power. But now it's screwed and it should be rigid enough when we put screws here. Now, should we use the same ones? No, let me actually go and see what else I have. Actually, if anyone wants, I can show my screw rack. This should be good enough. Let's take 20s. Also, Nidobu, even though you have a rest day, like, isn't it like incredibly late at your place? It's very important to sleep well before the exam. And don't ask me how I know, so you probably should go to sleep instead of watching my stream. No offense, of course, no offense. I appreciate it being here, but sleep is very important. Okay. So it looks like you bound to bed soon enough. Uh-oh. Where is my bit? Is it working? It is working. Nice. Okay, should be good enough for this test. And should be good enough as well, but I think I put it sideways. No matter. Okay. We prepared our first test weight. I know, now I know what happened to the 3D printer in the beginning, because I forgot to remove the parts. Oh my god, I'm such a dumbass actually. I know what happened now. I usually sleep at 1 to 2 p.m, so it's nice. It's not that late. Haha. Yeah, I'm thinking about changing my sleep schedule, but sleeping early makes me think I'm not studying or productive for career prep. And when like, what time does your study start? Because like, it doesn't matter the time you go to bed at, as long as you have the same amount of time in your day. It's just a perspective, like, question. Like, I'm not saying how you should behave, I'm just curious. Because I have no idea, like, what your situation is. And, like, some people prefer early sleep to be productive, some people prefer late sleep. Sorry, I have a phone call, one moment. Sorry, my card got blocked today. I can tell the story about it, so I had to talk to my bank to get unblocked. Okay, so it's not fixed, but when laid down bed, I usually watch cool stuff on YouTube, I read some books, and fell to sleep. I see. And remember to put rest high up on the priority list to actually function at your peak. fully agree with Onion. A lot of people underestimate rest because for the few days, like if you want, guys, we can talk. But rest is incredibly important because our bodies have a mechanism at which if you have like low rest. Did you buy too many electronics so that bank had to pump? Actually, that was that was actually almost what happened. I will tell the story now. But first about the body functioning. So the body has like limits and has mechanisms, and so when you don't sleep well for one day, sometimes you can actually feel even more productive the next day with like no sleep or limited sleep than you felt the day before. So you can feel high focus, high productivity even, but the problem with this it's that it's very fake, and you will feel like the fakeness of it when you will have to sleep after this, and you will have to recover from this because like you run on reserves if you have any, and also your memory sucks, and you will not remember anything even though you think you can be more productive and stuff. So high rest, or at least high sleep, I don't think that you necessarily need some specific rest schedule, rest procedures, but sleep is very important. It's incredibly important. So I fully agree with Onion here. Also, you work on this project as hobby or part of professional work where you work. So many topics for discussion. Currently, I'm unemployed. Not really. I have a small business. I work as a freelance engineer. I just currently don't have a client. And I don't have a client for 2 months. And I thought to myself, I'm not really in a rush to find a new one, or at least I wasn't before. So I decided I would love to actually finish this project properly, maybe go even further. And I thought, why not try streaming? Maybe it will go somewhere. It doesn't seem like it's going somewhere. I think not that many people are interested in what I'm doing. But yeah, and the interesting story as well is that I will need to move to Germany probably next week for like 4 weeks. I had a new client, that asked me to come and go help develop and bring up the electronics and firmware for them in Germany. So I will probably not stream for a month starting next week because I will go to work. But yeah. Not sure. I thought I would like to say something more, but I don't think I would. Regarding the card situation. So I got my card blocked when I ordered from DigiKey. I ordered components for the encoder PCB. Actually, the encoder PCB situation is hilarious. So first, I have a person in China. It's like a special type of company. There are quite a few in China that help Western companies, Western people to find suppliers in China for their needs. So with my previous client, we worked actively with this person, and it was like he was very helpful. They were like helping organize the whole production chain for the products, like physical products. And so I was occasionally doing small orders with them. So I placed an order for my encoder PCBs with them to see, like, compare the prices. But I got $120 for like 5 PCBs assembled for 5 encoders, which are like small boards. And I was like, hell nah. And this like was plus shipping and plus taxes. It was like $200+ for like 5 boards. And I was like, oh, what is that? So I actually ended up ordering with PCBWay for $80 for boards and stencils and assembly. So everything, like 5 assembled boards and 5 unassembled boards. It will just take like 4 weeks or something. And then I thought to myself, hell nah, 4 weeks, like if it's 4 weeks, I will never get the boards. So I also ordered the boards again, but not assembled, and I ordered components separately, so I will have 2 separate orders of the same boards. Once will just be assembled like in a month, and once will be unassembled in like next week probably. So yeah. And yes, I was ordering components for boards from DigiKey because DigiKey has decently fast shipping, even though ordering from LCSC was much cheaper, but their shipping prices are rather high if you order small batches. It was better before. So the price of components with LCLC shipping was the same as price of components only on DigiKey. And the LCLC shipping was like $30. So I decided, okay, I need speed and I need components, so I will rather order from DigiKey. And then I ordered, and then my card got blocked. And my card got blocked like at 12 today, and it's like 8 almost. So yeah, I was waiting for the whole day for bank to call me. And then they called me, and now my card is unblocked. I can continue spending money on electronics, I guess. But now I need to think about like preparing for my trip to Germany for like the work months. Anyways, let's go and start working on the gravity compensation, shall we? Okay, so we need to assemble the test stand. So let's do it. I don't like this stand. I actually have a more beautiful one. It's blue. So let's move the motor. Our encoder is correct, so it should be a little bit of screw driving. Uh-oh. Okay. Go away. And where are my tweezers? Okay, where are my tools, actually? Someone help. What is the size? Oh, this is the size. Okay, and where are my tweezers? Hello? Oh, here they are. Okay, one moment. Let me disassemble this. Actually, I can do it by hand without the need for Allen key at all. I myself found myself in a mobile authentication limbo as I was trying to enable mobile auth on my SIM. The registration error out because phone number already has mobile auth, but when I try to log in using mobile auth, they say number doesn't have set up. And how did you solve this? Were you able to call someone because like you were working with your SIM? Like, did it allow you to? Or were you like completely stuck? Door stuck. I didn't. I will call the support tomorrow. I see. That's unfortunate, actually. But I hope you don't need your phone for anything. For anything urgent list. At least you are able to buy your snacks, you know, when you have your card blocked. You are kind of paralyzed. It's nice that I do a meal prep and I have like food for like 4 days at a time, all the time. Or I would have starved today. The phone works fine. It's just stupid that I pay for mobile auth and I am logged on immediately. True. Very true. Also, you were talking about it and I just remembered things. I don't know what happened today specifically, but like software just didn't work for me today. I don't know what's happening, but I think I had YouTube issues. Like YouTube was like lagging. It wasn't resizing correctly and it wasn't loading correctly today for me. I also had some other website not opening at all. Like it was so weird. Oh, and I had also Fusion 360 problems today when I was modeling the gravity compensation crank. So it's like, what the hell is happening with software today? Okay, we're finally out of here. Holy, we made a dent when we were testing currents. Holy, because this is supposed to be flat. Let me show you. Actually, very interesting. This part is supposed to be like this. It should be flat. And this is the result of us pushing 5 amps through the motor, I would assume. Okay, all right. The motor, oh, it's also bent as hell, actually. I'm not sure how it's seen. But this part was damaged. We're entering the NMS vibe coding software era. True, very true. Okay, so this is one of the ways to like press forming PLA, I would assume. Hello, multiplexer. How are you doing? Welcome, welcome. So let's use our new victim, I'd say. But I think we will not see problems with denting today because we will push way less currents than we pushed during our constant verification, a mechanical constant, torque constant. So current today should be within 1 to 2 amps because we will not need more torque than this. Well, I'm doing well, dealing with some personal stuff, but otherwise fine. I hope everything is fine on your personal stuff, things. Like, feel free to cry in the chat. We will listen to you and help out if we can. I'm doing pretty fine. I was doing a debug protocol update that was supposed to be 1 day, and now we are 3 days in, and we are only halfway done because every day I just think of new ideas. But today I decided to do something different because I would assume people are annoyed by me working on the debug protocol. So today we're testing new motor control stuff. The onion, I just realized the other day I can use the 3D printer hot end to push down threads, insert into prints. It's obvious. Oh, actually, hello. This sounds interesting. Push threads. For this, I personally have a kit from CNC Kitchen. I actually like it. And actually, also another funny story. Today's a day of funny stories. One moment. I will be fine, thank you. Love to see mechanical engineering here. Yeah, I was doing quite a lot of 3D modeling before the stream to prepare for gravity compensation testing. So this is what we will use. That's what I'm printing right now, so that we put the weight in here and we will use it as a crank. So I use these boys for pressing my inserts into parts. I actually like them a lot. They are very useful. And they are not that expensive, actually. And the funny thing is that I have an old, not old, but cheap, very cheap Chinese soldering station that was like $60 probably. And it has a single purpose. And the purpose is to use those when I need, to, because my high-end soldering station just cannot use them. So, and to know it, buy like a $300 soldering end to like do this on my station. I just have like a $60 cheap Chinese station to just press inserts. Okay, so let's finish assembly real quick. Any other stories from you guys? I'm quite enjoying today a chill talking stream while trying to do advanced motor control stuff. Oh my god, this will be annoying. I actually also, a funny thing, I figured out that this motor isn't supposed to be connected with a screw from here, but the screw from there. And because it has like this end. But I figured it out like after I already designed these holders, so I have to struggle with trying to hold the screw so that I can screw in the nut to not need to print a new version of the holder. I recently bought a FNRSI HB02. I'm relatively new to soldering, and so far I'm loving it. Let's actually see what it is. Let's see. The whole chat will see what you bought. The whole chat will see. So images. Okay. Oh, okay. Sure. I see. Yeah. Oh, that looks useful for like on the go kit. That looks nice. Okay. I think it's a nice buy. And how expensive was it? It's a USB powered standalone soldering iron. I don't have a workshop place, so I need to use something small in my kitchen. I got you. When I was like in the university and I didn't know how to solder properly, I like bought like a thick like this soldering iron because it was cheap, and I tried to use it in my kitchen, and I think I almost got my kitchen on fire while learning this. So after that, I decided to do some learning beforehand to not repeat myself, to not burn my kitchen down. Okay. Whatever. We will not need these screws. I cannot do it on stream. That's annoying. 2 screws is enough, right? So let's attach our weight. Let's remove our pin. It was on discount when I got it. I see. Things are always better on discounts. I would prefer something USB powered also. Granted, I need an iron maybe once a year, but hopefully more soon. I would like to learn basic PCB design. I see. But actually, when you do a PCB design, like soldering iron is also not as useful. Let me show actually. One moment. I'm sorry in advance for how my house looks, but like this is my soldering table, and as you can see, when you need to work with PCB, you're always better off not doing it by a soldering iron, but by having something like this. Leaked. Uh-oh. Okay, it's happened sooner than I expected. How do I turn it around, actually? Was? Work. Okay, one moment. I have technical issues. Okay, now it's working. So, anyways, what I was saying, that this part is a soldering table, and it's very useful when you solder PCBs. So basically what you do is you have a board. Let me show. You put components on it, and like when you're done with like soldering paste and stuff, you just do it like, and then it solders nicely. So, but it's also not as important when you only work with small projects and stuff. Like hot air gun will be enough. Only works for surface mount components, right? Yes, correct. So if you need to do a lot of THT, and also if you need to do a two-sided boards, you will have to use a different approach. This hot plate was actually Chinese cheap one. I think it's like less than $100. I would imagine it's like 80. So actually, let's just Google it. It's ET10. ET10 mechanic. So on AliExpress, it's actually $40. It's actually $40. So it's incredibly cheap. So if you need one, I would highly recommend this. It's terrible thermal control, but you don't need a nice thermal control when you do prototype boards. You just put it to like 140 degrees. And when it gets 140 degrees, you just turn it off and put your boards on. And like you have good enough quality. It will just, because of the thermal pair inside of it, it will overheat and then it will cool down. So if you turn it off like at 210, 220, it will just still get to like 260, 70 and cool down. Yeah, like $40 is actually incredibly cheap. I thought it was more expensive. You need the plate flux and what kind of solder do to PCB. One moment. I need to ban a person. I did. So, you need the plate flux and what kind of solder to do PCBs. Actually, let's do a small explanation on how to do PCBs in real time. So let's see. Let me get my setup here. Okay. So, what do we have here? When you order a PCB, for example, you design a PCB. This is a very simple one, so it will be a very nice example. So, first of all, make sure you store them correctly, because when you order PCBs and components, you will have like a lot of them. You will have like a lot of them, and like, trust me, a lot. Let me show you. You will have a lot of components lying around. Can I make the camera bigger? I can put it further, I guess. How do I do this? How do I do this? Let me see. Oh, camera bigger, you mean on screen? Sure. I'm a dumbass. Okay. And let's also... And also... a bit further and more light here. Looks decent enough. I guess, I hope. Sure. So now, peace. You design the board. Let's say this one. This is a very simple board. It was test designed for a brake resistor. It's like basically like 6 components. 6 components plus connectors. So what do? When you order your board, first of all, make sure that you always order a stencil, because you need to have stencil to like solder them. And stencils come like this, but without these parts. So they come like, let me show you. They come like that. And this is the stencil for this PCB. So this is just an aluminum sheet that you will need to use to apply your solder to your PCB. So you will have a piece of this for every board design you have. And you can solder as many boards as you can with one of those. Well, technically is incorrect. They have shelf life, so they will break with time. But you can solder like many boards. Like way more boards than you will be able to solder by hands, you can solder with a single one. Now, let's say you got this. You ordered your stencil, which is this part here, and your board. And you also have your components nicely like lying around in like organized space. Well, let's see. This is another box of components, and these are all components for like this project. They are all in the same place. And let's say you have your components. Okay. Now, what do you do about it? Your best option, and why do you need to have a stencil? This is a custom designed rig that I use to apply soldering paste. I just can install a board here, close it in, it snaps, and now, actually, I aligned it incorrectly. It's supposed to be like this. You snap it in, you put it in, and you have the bus. Maybe it was for the other iteration of the board. Let's actually see. It says nothing useful. Anyway, it should be aligned. So as you can see, let me open one more. Your pots, which are silvery things here, these are pots. They all should be aligned with holes on the stencil. And yes, it's definitely a stencil for another board because I don't see enough holes here. Oh, actually, hold on a second. Am I mixing different iterations of the PCB? Oh, yes, I do. I'm an idiot, actually. Also, a very important part, mark the iteration of your PCB to not be me. As you can see, on the left we have I1 and on the right we have I2, and they are different designs, and this stencil is for I2. So that's why they were not aligned, but let's now use proper correct PCB, which is I2 of course, and let's put it in our holder. So it is there, we insert our thingy, and now they are perfectly aligned. So as you can see, I can only see my pots, like only metallic things, aligned correctly. And this alignment part is actually very important. You need a way to align this correctly if you want a good soldering quality. So this rig is actually a very useful tool. I can share, I think, 3D model design because they are very simple to do, but incredibly important, incredibly useful. So now that you align this, what you do next is you take your soldering paste, which you probably should store in your fridge because soldering paste needs low temperatures, but I didn't. So my soldering paste is kind of messed up, but they are usually like good soldering paste comes in such buckets. Oh, it smells terribly. I think it's past its shelf life. Yes, and you get your paste, and then you need another important tool. You need a card that you will use to, as spatula, I guess is the right word in English, to like apply the soldering paste. And it should be very flexible. I have no idea what this is actually, Smart Island. I have no idea what it is, but it's very flexible and it's very nice. And before that, I actually used my old credit card that was out of date because credit cards also have a nice flex. No, the card doesn't have to be of Smart Island, and I have actually no idea what Smart Island even is. But the card is awesome. Thank you, Smart Island, for the card. Hello, Mr. Das. So now, let's actually do this. Now you need to apply your soldering paste, and the problem here is that if you don't have good tension here, or like this, it will bulge, and if because of the bulge, you will apply too much soldering paste first, and then it will also like mess everything up. So if you have a terrible paste like me, what you do is you need to first mix it. So you go and take your mixing tool. One moment. Let's say a chipset like this, and you get like something. You open your paste and you just, oh, it's so, oh my god, it's like heavy as stone. Oh my god. But I think it's fixable actually. And to fix this, holy cow, I need a new paste. We can put in some flux. So flux, and good flux is also very important. And you can just put some in. Let's say a bit. Can it be seen that I put, oh my god, some flux in, and now I can try to mix up a small portion of this container to have a decently liquid paste. So let's actually try to do this. This is how you fix a very stale soldering paste. Don't do it if you have option to store your paste properly, but if you don't and you are dumbass like me, mix up a small section of it so it is liquid enough. You will, even if you have a nice paste, the flux tends to settle down with time, so you will need to like shuffle it a bit anyways. I can't believe flux is such a silver bullet in electronics, good for soldering, adhesion, solder cleanup, solder paste fix. Flux is MVP. It is. It's definitely an MVP. So this is liquidy, but I think I need a bit more flux here to make it usable. So let me add some more. That looks kind of nice. So let me mix a bit more into the mix. Sorry for the prompt of design, but this looks nice because I actually would like to show the process correctly. Also, if you plan to work with this properly, buy yourself a huge like bottle of cleanup solution, like something like this that you will be able to like clean your boards with. Actually, I don't have a mark here, but it's like something alcohol based so that you can clean your boards. You will use it a lot. Trust me, especially in the beginning. You will need to clean a lot. So, let's say we have somewhat a liquidy substance. Now what we do? We take a bit of it and we put it on our board like this. It should be liquidy enough. Now, where do I put my tools? I wasn't ready for this one moment. It's like 99% alcohol. I don't think it is, but it should be alcohol-based because it's generally useful, not only for PCB. Like there are probably better solutions for PCB specifically, but alcohol-based, like yes, as Mr. Das said, are just nice. So we have some paste on our stencil, and as I said, the important thing here is to have our stencil aligned and under tension. Because if you will not have it under tension, you will have bulges, and bulges are terrible for quality. So you just get it. The screws are a bit loose, so let's tighten the screws. And where is my Allen key? Yeah. So let's tighten the screws a bit. This is too big. And this is too small. And where is the correct one? One moment, one moment. This is the correct one. So, oh no, my alignment is broken. Oh no. Now I have to realign this. Oh no. Actually, it's almost there. Okay, it's actually nicely aligned, so let's... Sorry for my hand view. Okay, this is not the right one. This is the right one. So let's fix it in. Like that. Should be good enough. And now I can pull it down and use our Smart Island card to do what? I'm pressing and I do like zhuch. And this is not liquidy enough. Oh my god. I needed to add more. I needed to add way more flux actually. This goes awful. No. Oh no. This is awful. Oh no. Yep. Never enough flux. One moment, one moment. We are fixing it. We are fixing it in real time. Live on Twitch. Okay. We are almost there. I think this should be liquidy enough. What the hell is this? One moment. I think it should be alright. Right? Don't be a mess like me. So let's see. I hope it works better. Oh, yes, it does. So you hold it under tension and you apply it. And your goal is for, like, it's still not enough flux, but it's like decent enough. Like in perfect world, you will just do it once and it will work. But given that I don't have enough flux there, like I had to do it like a few times. Now, important part is here. You want to also, a part of the design of this holder is that I can do like this and I can lift up the part there. And now we have our PCB with soldering paste applied everywhere. Oh my god, it's not applied everywhere. And because the flux, we haven't had enough flux, we had this issue. When our soldering paste got stuck in a small pin. It's door stuck. But with like liquid enough soldering paste, you will not have like this issue. But because of it, we have soldering paste applied almost everywhere, but not here. Not in this place. But let's assume that you are not a dumbass and you did it correctly. What you do next is you usually carefully take your tweezers. Where are they? Where are they? Where are they? Oh my god, I'm such a mess. Hello? What? I'm in danger. Where are my tweezers? Us. I'm making a list of what to not to do. Yeah, true. Okay, kids do as I say, not as I do. Yes, exactly. Exactly that. Oh, I found them. So you usually go here and you just pull it up. And you usually put it on a mat like this. you usually have it organized on a table, of course, and also cleaned. So what you do usually is you, in quick succession, apply like paste for as many boards as you would like to assemble. Let's say it's like 4. They all have paste at this point. And mats like this have like holes for components to go to. And you just put your resistors, capacitors, anything. And now you go through things and you just put carefully your components one by one on the SMD first. So you do all your SMD placement, and it's very useful to do it component by components, like first on all the 10 ohms resistors or something, like on this board, on this board, on this board, and on this board. And then like capacitor on this board, on this board, on this board, on this board. So one by one, then you have all of them ready. And what you do next is, as I said, you heat up your table and you do it like And the big deal with the table is that you can actually use tweezers if your components are not perfectly aligned, because when solder melts, it creates a surface tension, which helps to align components. You can use your tweezers to move them around because you have access to. And then you just put them back to a place where you can put hot things to, and you just let them cool. And when they are cooled, when you have a board that is fully soldered with SMD components, only after that you manually solder like your connectors and everything that is through hole you have. So soldering through hole stuff is the last part, the last step. Thank you, Nirbu, for being here. Good luck, or rather, go get him, Tiger, on the exam tomorrow. And I see you in the next one, whatever it will be. So this is a basic one, and now the most important part of any soldering job is to actually clean up. So you take your solution, you like and you clean your stencils, of course, because if you want to solder more boards, stencils cleanup is very important. And yes, in the manual production at home, you will have a lot of residue left. So you will waste a lot of paste that is still on the card. For example, here, like you can put some of it back to the box, but not all of it. So you will waste some of it. And here we have still our solder stuck. So let's clean this out on both sides. Make sure that you clean both sides, because if your tension wasn't perfect, you will have like small islands of paste on the other side, even though you expect there to be none. So make sure you clean both sides every time. And you can use like how's it called? The paper that doesn't have like these things. That's like splits into like clean sections, not leaving small strains. So you clean this up properly on both sides, of course. Make sure you don't leave anything for the next time. You clean your Smart Island card. And you can also do it like this with your applied solution, cleaning solution. And both sides as well. And then you just store everything like in the bag or in the box or wherever you want to store it in, and you have your boards assembled. And the next part is, of course, bring up. And the bring up is another like thing. Don't expect your first burst to work the first time. So the process of bring up is actually a process of testing functionality of your boards in a small safe steps before it works properly. Because if you try to run your board in nominal conditions the first time, even if your design is correct, which you have no guarantee in unless you have experience, even if your design is correct but your soldering isn't, you'll have issues. You can blow up the board, blow up components, like blow up your life expectancy and stuff. So don't do it carelessly. Actually, one moment, I will also need to clean this mess. One moment. I'm almost done. Cleanup is a part of the assembly process. So you do continue checks before you power the board, or what do you mean? Let me explain. One moment. I'm finishing my cleanup. Okay, so this should go here. What? Oh, I see. Oh, okay, whatever. Whatever. No, not whatever. So let's see. Let's imagine that this board is assembled, and to imagine this properly, let's say this board is assembled. Boom. Let's imagine this board is assembled. So first you check with your multimeter that your power supply is not shorted. You need to check your power in and ground and all power sources. For example, on this motor driver PCB, I have V bus here, 5 volts here, 3 volts, 3.3 volts here, and 3 volts here. So you do, and you check with your multimeters that they are not shorted, none of them. Not only ground to any power source, but also any power source to any other power source. So this is important, and this is what the manufacturers do in reality. They check many points, and this is called a flying probe test. And I see that my camera is broken. Uh-oh. So you do like a shorter version of a flying probe test. You test the power supplies. Then you can also test critical components. For example, you can test if some passes of outputs and inputs are not shorted, but this is you decide based on the design. Then when you do, the first thing you do when you connect your board to the power is you set a current limit. So here, a moment, you set the, let's remove it, the minimal voltage your board can work with, for example, 12 volts. And you set a current limit at which you're sure that the board will boot up, but small enough so that if you have a short or have a miss connection somewhere or design flaw, that your board will not blow up. Because sometimes reverse connections and short circuits are not damaging if you don't have enough current flowing through them. So your first boot for your every new design is a boot with a very low current limit. So you do the boot, you test that it works, and if it works, you can safely increase the voltage to like your nominal, let's say 24 volts, and you can increase your current to a nominal, for example, 1 amp, and you can test functionality of the board itself. But these are important steps. First, you do multimeters, and you do minimal voltage change test, and then you like escalate the complexity of tests one by one. And trust me, if you will not do it in a proper order, if you will be very confident that it's an easy design, it will work, you will blow up some boards right in your face. Anyways, that was an hour long, how do I call it in English, actually? An hour-long rendezvous, I don't know. So we wasn't supposed to do this, we weren't supposed to discuss it, but we did anyways. And it was fun. If anyone have any questions, ask, I will try to answer them. Let me continue clean up in the meantime. Yes, and board identification is very important. Like these two boards look identical, but they are different. And how do I know? Because I know the iteration level is different. So I know they're different, even though they look like the same. And always store the boards correctly, only store them separately, iterations by iterations. Or rather, for boards, it is called revision usually, but I use word iteration because I use word iteration for both mechanical and electrical work. And to have a continuous system that works for everything, I usually call everything iteration rather than revision for boards. Yeah, indeed. And generally, when powering for the first time 0 amps, something is not connected correctly. X amps should be functional current limits, either current limit to low or short measured with multimeter. Yes, exactly. So let me finish the cleanup so that we can finally go and do gravity compensation, shall we? Okay, so just a little bit more. So what iteration are you? You are 2 and you are... Oh. 2 as well, and you are... 2 and you are... 2 and you are... 1! We have an intruder.
Multiplexer tipped $5. Thank you for being such a wonderful and dedicated teacher. I really appreciate that my small question got you to showcase the process. I learned a lot.
Thank you so much for $5, Multiplexer. I appreciate it so much. No worries at all. I had fun discussing this, even though it was a complete mess. I'm sorry. But actually, I am leaving for a month to Germany for a client in May. But when I come back in a month, we will do a soldering stream. And then I will showcase the whole process properly. So tune in a month for a full-on hands-on demonstration on how to do it, and also to learn from my mistakes to not do your own ones. And thank you so much for the donation. So much. Okay, so this will be cleaned. One more moment. Okay, I think we can proceed with our gravity compensation, I hope. So, let's finish assembling this boy. Oh, I think I have a finished part. Let me go and check my printer, one moment. So this part is for this boy. Whoop. Oh, that was so satisfying, actually. Okay, I'm done playing. One more time. Okay, I need to put one more part printing, so let's do it. Which one? Which one? You. Print. Send. Okay, okay. 13 minutes. Sure. We can wait for 13 minutes. Going. Okay, whatever. Now, this one will wait for its lead. And in the meantime, we will work with a smaller one. We have 100 grams here and 200 here. So, that's a nice software tool. It is. Bamboo Lab Studio is actually incredibly handy, incredibly usable. I like it a lot, actually. Even though they have some controversy with like personal data and stuff, like the software is good. I actually personally, I'm not sure that I will air the notion, the idea that many people have, but I think that Chinese tools, Chinese hardware, Chinese technology is incredibly impressive nowadays. Because I was a kid in the times when everyone was considering Chinese products to be like a joke. Everyone was saying, oh, it's from China, then it's complete garbage. And a lot of people, a lot of older people still have such a mindset. But when you look at some Chinese technology, it's like, holy cow. So yeah, I do respect Chinese tech a lot. And Bamboo Lab is just one of the examples, as DJI as well, of companies that are very impressive in China. So, we are almost pressed. Very nice. And let's add a screw here. Actually, if you want to see my screw collection, it's like da 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 da. China does everything in the modern world, so they have a whole range of quality and products from the best of the most shit ones. True, very true. Actually, very true. The difference is that 10 years ago they only had shitty ones, and now they have good ones as well. So let me go and fetch a screw. One of them. So, let's try with the longer one first. And why do I have them both in boxes and in packages? Because given that this setup, if things fall, you will suffer a lot to sort everything again. May I ask what you do for work? I am, currently I don't have a client, but I will have it like next month. My client first in 3 months, 2 months. Actually, I didn't have a client for 2 months, but I am a freelance outsource engineer, and I work with electronics design and firmware development, and I also occasionally do 3D modeling if needed for like minimal stuff, but I mostly do electronics design and firmware design. So, and like the last client I had for like 3 years almost, and it was heavily product oriented. We were developing products, and so they had not especially, but rather 3 years ago they had a very good situation. It was post-COVID, and they were a company that benefited a lot from COVID. So they were rather rich at this point, and they were investing heavily in developing products. So while working for them, I managed to buy a lot of equipment for their money. So most of the equipment I have on my tables is like bought by them, like 3 years ago or so. And so we were developing products, and I managed to like stock up components, electrical components, mechanical components, and stuff. But now they are very close to being bankrupt. So the company is around bankruptcy for a year already, and so I currently don't have a client because I was let go due to their financial situation, and now I have a new client. But before it, I just decided to try to stream and see how it goes and showcase my terrible engineering skills to the masses. So here we are. Here we are testing our gravity compensation. Right. Now, so we have our mass attached to our shaft, and we need to let it fall. Ta-ta-ta-ta-tum. Okay, very nice. So let's see, it should be able to rise. Very nice. So let's attach it to the table. Thank you for starting the streams. I really enjoy them. Thank you for enjoying my streams. I actually was afraid that Noel will be here at all and Noel will be enjoying it. But given that I literally have like a few people coming almost every day, I'm very happy with doing this. I hope people are learning something or at least having a nice time here. You got a day rate, or is it based on the project? That's a good question. That depends. I'd say it's based on the project. So if I like the project a lot and if I have like desire to work on it, maybe I will charge more or charge less rather. But if I just has to do the work that's like I know how to do, but I may as well not really enjoy for the people just as outsource, like pure outsource, I will probably charge more. But that's highly depend. Like it depends a lot because I was lucky in my life to be able to work long time for same people like multiple times in my life. Okay, so this looks kind of sketchy, but it works. Okay. So yeah, I'm not sure the exact answer. If you have like a proposal for me, feel free to send it to my email. I will look at it, but I don't have like a fixed answer that, oh, I will charge you for your life savings if you need to work from me. I'm not sure. It's like highly depends. You already did the face reveal, so you are speedrunning the test streaming. I will actually remove it from the VOD on YouTube because I am ashamed of myself. It was an accident. Okay. So, here, what do? We need to attach our controller, so we turn off the power supply and we disconnect this motor and connect that motor. So let's do it. Let's see. Okay. What do I need? I need a flat screwdriver. You do not have to be ashamed, but I understand wanting to stay anonymous. True. Very true. Okay. And here. And here. Like this and in quarter. Thank you for understanding. Maybe I will reveal my face properly later, but for now, I'm not ready. Okay, so let's remove the USB wire. Let's attach our encoder here. What encoder are you using? I'm using a Chinese part that I had no idea about, and I looked up with my previous client. It is an empty. Let me actually just show you. It will be easier. Where the hell am I? Oh, yeah. Let me show you. Let me show you. See. Study this one. And I will paste a link in the chat if you need it. It is a very cheap part compared to many, and it has a nominal 21 bits, which is absolutely insane for a magnetic encoder. It is insane because all other Western, it is a purely Chinese part. And I know such parts because I worked a lot with Chinese suppliers for my last client. Not a lot of these parts, but I worked with parts like from China purely. But for the price of this part, which is like $1.8 for 1,000 for a magnetic encoder, this is insane for 21 bit. Because let's Google like other parts. I don't even remember them. Let's just chat GPT them. Magnetic encoder IC part numbers. Let's look. This one probably will be insanely expensive. $11. Holy cow! Was. So what else do we have? IC house. IC house even more expensive. What is that? Also $5 and 3.6 at 1,000, and only like what is the resolution here? 14 bits. So you get 21 bit here for like 1.8, or you get 14 bits for like $3. And yes, 21 bits is too much, so you don't have like actual 21 bits, but when you need an approximation, it's like just a hardware approximation of your bits, and this is like incredible. This is incredible. So I highly recommend this part. Even though it's unknown, it's like pure China, but it's very useful. It's incredible for what it can do and for what the price is. It's probably not a super industrial grade, but for what it can do, it's like, oh my god. We use optical encoders, high precision, so our encoder are like $30, $50. Oh, I can imagine. I can imagine. And what do you actually do with these encoders? Like, what are your systems? What are you working on? If I may ask. So let's get back to our assembly. Let's put it in. And let's screw this in. Okay. Why is Chinese components so cheap? Is just cheap human labor, or are there any drawbacks? First of all, I think the most important part is not a cheap human labor, because Chinese labor is kind of expensive right now. Because as I said, given that I worked with Chinese for like 3 years, last 3 years, and we were using their development services as well sometimes to help us, they charge a pretty like hefty rate. Their like leader, manager charged like $50 per hour, and their electronics engineer charged like 30. And this is a respectful European rate for like beginners and like middle engineers like freelancing. So they charge decent money and they got paid decently. And for components and for a lot of factories, the biggest thing, in my opinion, and I'm not an expert in logistics, but in my opinion, it is a supply chain. Like, they just have everything available locally. They have connections. Because you can come to Shenzhen, you can order PCBs and they will be on your table the next day. You can order components, they will be on your table this day. Like, this is insane what you can do in China, like literally. And this is part of the reason it's cheap, because everything is established. You have established logistics. It's almost zero. You have all the materials, raw materials there all the time, and they coming there all the time. So everything is there. And yes, when we work about low education level workers, their hourly rate is lower compared to European rates. like compared to even Eastern European rates like Estonia, Latvia, which are considered still to be like very cheap as well. So like uneducated rate is also low, which is true, but you cannot do microchips with low educated manual laborers. I don't think you can work in a fab without having like a degree, at least like a college, not a college, like a professional education degree, which is not like university but lower grade. Would it be crazy to build European Shenzhen to have the whole supply chain in a single city? I think the biggest problem with this is just that many countries will probably would like to hold it, would like to host it rather, and like people will probably not agree much that they, for example, needs to go there. And also legislations in Europe is very tight. For example, Germany would be probably a place to put such a hub for many, but with German laws, I think it would be a suicide to organize this, because zones like Shenzhen have to have a lot of law, not restrictions, but what is the opposite of the restriction? Like some limitations, some logistics limitations, some purchasing limitations, some like VAT things should be like lowered, should be removed for such a zone to work. I'm the embedded lead firmware engineer of a company who makes high speed and high precision ultrasonic piezoelectronic motors and stages. Oh, that is also how I found you, but I'm enjoying it. Oh, I see. So I'm embarrassing myself in front of experienced person. Now I have even more pressure on my shoulders. Okay. Uh-oh. Okay, let's touch. Yeah, not at all. Okay. Sure, we're here for fun. Some of you are, and I'm sweating here on the other side of the camera. Okay. Let me screw this in. Hello. Please, mister, go forward. Very nice, very nice. And this as well. No pressure roll. Okay. I'm joking. No worries. And here. Screw this in. Let's check if they are all attached properly. They are. And everyone expect a climax now, but our software is not ready. So let's get back to our IDE and actually implement the gravity compensation, because we don't have it implemented yet. And that means that I need to switch screens. So now let's do it quickly. Gravity compensation shouldn't be so complicated, at least I hope so. Now then, we have, let me see, 200 millimeters here, and we assume this part weighs like, I don't know, 10 grams. I'm terribly sorry. And we assume that our weight here is 100 grams. So this is, let's open our drawing. Like here. So we have, boom, bam, 200, 0.2 rather. We use CI units, of course. And we have a mass here that produces torque. So our torque will be our mass, G, and 0.2. So our mass, let's assume it will be 105 grams. So we can calculate that the torque we need to compensate for is 105, 981, 0.2. Let's open a calculator. So, but this should be 0.105 because we use NCI units, of course. 981, 0.2. So we need to produce a torque of 0.206. And this will roughly compensate our load. Now, Okay, let me use different color. So produce this torque, Newton meters. Okay, let's go to the firmware side. How do we do this? To produce a torque, we need to clean up our mess, but we will do it later. Let's just, we did our motor parameters identification, and during the identification, we figure out what that I need to go and look up the table we actually made, because I don't remember the value. So let's open it and let's see. We defined our torque constant as this value. Very nice. So let's define motor torque constant equals to, not equals of course, don't be silly, F. So this is our torque constant, and so when we need a torque, so let's check. We should be in the current control mode, and we are in the current control mode. So nice. Let's set our current target to 0. And also we don't store the calibration values, so we will need to fake it till we make it. Okay, no worries, no worries. Because I'm rushing a bit too much. Let's set it to 0 by default. Now, with this being set to 0, what do we need to do? We need to wait for the motor to calibrate. And at this point, when we are in our current controller, let's switch to a better view. So we calculate that electrical angle. I need to go to make some food. I'll be back later if you're still on. Sure. Thank you for watching, and bon appetit when you are done with your food. If I will still be on, tell us what you've cooked. We can share recipes as well. So, now, here, we calculate our limits with our newly implemented space vector modulation, and we need to decide our current task. And when do we set a current task? At what point? Here. So here, let's say, first of all, we need to know the mechanical angle. Do we know the mechanical angle? We do. So, but we never store it as a radians value. Let's do it at the radians value. Plot mechanical angle. This will be a mess. Radians equals to our device in quarter m dot shaft position rho. Hold on, but how do we? Oh, I don't think we actually have a functionality to store a mechanical zero. Do we? Do we have it? No, we do. We do. We will just need to do a bit of a messy way to implement it. Okay, so let's do it like this. This will be current mechanical position within single resolution, so within single VSR. And let's say this will be our device quarter m dot mechanical shaft position rho. Reminder of the division by what? By MT 6835 was what? Hell, this value counts per revolution. So we get a reminder of this, and the mechanical angle in radians will be this value multiplied by MT 7835, and this will be rho to radians. And let's actually make this angle as a global variable so that we can absorb it in our you are working working here. Boom. Let's make it global so that we can observe it in our live expressions. Here, I will clean it up at some point, I promise. And now, let's test that this value is correct, because it will be very important for this value to be correct. And we will also need to store electrical and mechanical alignment. So now what I will do is that I will remove this part. We will do the calibration, and we will save all the calibration values to hard code for now, so that we can run example anyways. Then we will put this in, and we will be able to do the gravity compensation without calibration in the beginning. So let's actually do it. It sounds like a very good plan to me. Let me get my Allen key, and let me put this in. I selected 2 wrong Allen keys. There is always the third option that is correct. And where is it? Here it is. Let's remove our shaft extension. Like that. Un momento. This, and like that. Oh my god, it's so pressed in. Ow. I almost almost turned off my computer with my like stream is ending soon. Early today. Hello. I'm going to move for something. Brother. Okay. Now. Very good. So let's turn on the power supply. And let's let our motor calibrate. So we turn it on. And we observe the shaft. Okay, it did. Very nice. So let's see. Professional streamer, accidental stream power off is a rite of passage. I actually am most scared of accidentally leaving the stream on. This is like a fear I have. This would be oopsie daisy. Okay. So we should be in a debug mode, and we are not. So I'm a dumbass, and we need to do it again. Let's do it. I get that. That is worse. True. Exactly. So we are here, and let's run it. Are we calibrating? We are. So what values do we need to save? We need to save current values, of course, calibration. So let's do this first. This is the easiest one to do. So where is our current calibration code? It is here. So instead of this code, we will don't forget to uncomment when gravity compensation is done. And we put here the values that we called there, and they are stored in this array. This array shows us 11 and 12. So 11 and 12 hard-coded calibrations here. What else do we calibrate? We calibrate electrical offset. So let's put the value here as well. Align encoder to shaft. So here we will need to comment this out, copy this, and comment that, copy this, move it back here. The align, and we need to just actually put a hard-coded value that we currently store here. So let's open our encoder and our flux alignment. Where is it? This value. So we just hard code this. What else? we need to hard code these values, but do we actually need to do it? I would imagine that at this point, what we would like to do is we would like to use the value when the gravity is down, when the our load is stable, as a mechanical zero. It will be the easiest one. The easiest one to implement. So let's actually just implement this in code. It will be automatically selected then. So we remove the voltage alignment. We don't apply any voltage here, but we do a delay just in case we had any mechanical, anything mechanically offset during the last test, during the reprogramming. So let's put like a 2 seconds here for biggest mechanical vibrations to settle. And after this, we do our first reading. Yes, and this actually looks very nice. And I think this code should stay as is. So let's put our reminder here. And I actually think that we are all set. So let's actually test it. How will we test it? We will put a current task that is not big enough for the motor to lift up our load and see if the force seems correct. Oh, yes, it sounds very nice. So let's set our task to, for example, we have a positive rotation being counterclockwise, so we need a negative task so that the rotation is clockwise, because I would like to have it clockwise so that it doesn't hit the thing that holds it. And let's set the task in here as minus, let's say, 250 milliamps. It should not be big enough for it to lift the arm, but should be enough to lift it slightly. Now, let's then put our crank back. Put the crank back. A moment. Oh. Very nice. Let me screw in. One moment. Where is my Allen key? I lost my Allen key again. I'm such a mess today. Where is it? Hello? Where is it? Oh my god. Am I stupid? Am I stupid? Okay. Oh, I found it. It will be here. And now if I forget it, just reminded me that it's in front of the oscilloscope. But now let's flash what we've done and see if I am stupid. Let's flash it and pray that it works. So okay, let's get this up and this up, and let's see what happens. Oh, ooh, something happens. Okay. Ooh. Let's measure the angle, and for this I actually have a tool. Let me go and fetch it. One moment. Oh, if it already looks quite nice, you will be amazed what we will have like in 20 minutes. So this is a tool. I hope it has battery on, because I didn't use it for like 2 years. So let's see. It should tell us 0. and an angle. Very nice. So let's measure. What do we have here? Tell me. 70 degrees. Okay, 71. So let's go and do some calculations. 71 degrees. Does this make any sense? Let's do the numbers crunching. So our situation is as following. We have a shaft. We have a mass of M and length L under torque T. So our torque will be 0.2 amps multiplied by our KE. Oh, I'm so stupid. I'm so sorry. I'm so sorry. I'm so sorry. Sorry. Thank you. Thank you. What the hell is that? Oh my god, I'm so sorry. I'm like, what is going on? Okay. So I hope my math was correct. This is what we should supposed to get. This is actually not much at all. Interesting. And we have an angle theta here. And our theta is 90 minus 71, which is 90 degrees. So our force is as following, G, and we have an angle of 70 degrees, 71 here. So we need to find our projection onto this line and this angle. Okay, let's see. This angle will also be 71. So our projection will be G cosine of theta, period, right? Right, this will be a force, and we will also need to provide a torque. So this will be a force that is applied to this line. So let's see, it will be equals to 105 grams multiplied by 981 multiplied by cosine of 71 degrees. So let's calculate. Cosine of, okay, mass. Where is my Wolfram alpha? And let's put it like this and this like that. So, my dear Wolfram, tell me please what is a cosine of 71. Actually, tell me what is cosine of 45. It is correct, so it is in degrees then. And if it is in degrees, tell me what is cosine of 71. It is this now value. So this equals to this value multiplied by 0.15 multiplied by 981 should give us 0.335, and this is still in newtons. And to get a torque, effective torque that is applied to our crank, we need to also multiply this by our length, which is 0.2 meters. So let's do this. And this will be equals to 0, 0. Oh no! Is my GG correct? Damn! I don't think so. Actually, G constant at my coordinates. The location due to the gravity in Warsaw, Poland is approximately 813, 814. Okay. 8, actually, hold on a second. Was it with 0? 13. We will include this into calculations. Oh no, have I closed it? Whoa, what have I done? So 0.3 here, as viewers requested. Okay, so what is my result, brother? My result is 0.7.6, and this should be very close to this value, and they are very close, and this value is bigger because of the friction. So we are having a very nice and correct result. Very nice. So this value is supposed to be very close, and they are bloody are. They bloody are. So 0.0736, and we have 0.0767. So we have a difference of roughly 0.066. So this is a friction that will be in hold as a friction torque. Was your angle measurement correct? It was. It was. What is inaccuracy? I think it's plus minus 1%. But also I was holding it and you can see like even like a slightest push changes the angle. So we will not get like perfectly accurate results, but we're getting like good enough for the demo I plan. And the demo I plan will happen shortly. So we will use this as a value we will always add as a value we would need for the software to produce. So let's see. Also, we need to add an angle and see if the angle is calculated correctly. So where was it? One moment, I need a sip of water. Okay. So where is it? What the hell did I... Oh, I think I put it lower. Yeah. Boom. And the angle is... What is that? What? Actually... Okay, so... It kind of works in this direction and kind of doesn't work in that direction. Okay, very unfortunate. Very unfortunate, very unfortunate. How do we do it correctly then? What is this formula? I know the way to do it. It's not a beautiful way, but it is a way after all. So, okay, we will do like this. We will do this, and here we will do minus m 2 pi f32. This will work. Now, let's actually test it. Because I am confident enough, but not 100%. So let's test it first. Let's test it first, and let's run it. And it waits, and then it goes up. And now when it's up, it says minus 0.33 and 0.33. So let's see, 0.33 in radians. We multiply by 180 and divide by 314, and we get roughly 19 degrees, which is correct. We had 71 degrees there. So this is a correct angle estimation. We are getting very close. So, but this tells us 17 degrees, but we need a cosine of 71. So we will need to do a pi minus 2, pi halved minus this value to get the correct angle estimation. Very nice. Okay. So what we will do, we will go, I got lost again in my own code here. So mechanical angle, angle radians will be equals to m pi halved minus, hold on a second, is it correct? Is this correct? Will it work for every quadrant actually? Let me lift it up. So now it says 270, 240, and minus 240 is what? Let's say I hold it roughly at 45 degrees like this, roughly. And let's say it says minus 254. So now it says minus 254. Let's convert it to radians as well. So minus, okay. Hello, minus, no, stop, clean, minus, okay, whatever, 2.454, we multiply by 180 and we divide by 314, and we have minus 140. Okay, this was a terrible experiment because 45 degrees will be approximated correctly all the time, so let's actually use an angle that is definitely not 180, and let's actually use our tool. So we have it after all, right? 0. So let's assume that we would like to have an angle of 120, and let's see what our measurements say. So let's say, so 120 will be a 30 degrees then, which should be roughly this. And our measurements say minus 2.03. Okay. So minus 2.03 at 120 degrees. 120 degrees. Okay, and let's do the calculation. Let's do the conversion because angles are incredibly important in this scenario. So minus minus, oh my god, to 0.3 multiplied by 180 and divide by 314, and this gives us roughly, wait a second, this is a correct angle. Oh, right, it is a correct angle. Oh, so we will just use a sine, not a cosine, and we will solve the issue just by using sine function. Why am I bothering with angle conversion? Just use sine instead of cosine. Like, are you stupid? I'm talking to myself, I'm sorry. I will just use a sine function then. It's so easy. Like, why am I bothering with this even? So, now that we are here, let's say we would like to compensate. We would like to compensate the mass of... Actually, hold on a second. Why am I even calculating this? Am I stupid? Am I stupid? Am I? Hold on a second. Is my torque supposed to be different depending on the angle? It shouldn't. Like my torque should be constant, right? It doesn't matter what the angle is, correct? Or do I need to provide more torque? No, I do need to provide more torque, right? Yes, I do need to provide more torque. I'm just stupid. Oh my god. So, let's say float current command gravity compensation will be sine of our angle. We will use arm sine, arm sine of 32 of our mechanical angle in radians. And this value we will multiply by our mass and our gravity. So 0.105 F multiplied by gravity in Warsaw, which is 813. And what else do we need to have here? Oh, 813. I think this is it. So let's see our calculations on a piece of electrical paper. we used cosine, but we will use sine here instead, and this, and we also need to multiply by a crank length. Sure. So the torque we will need to produce will also need to be multiplied by this value. And we also need to divide this, because we won't like to have a current, and divide this by the current constant. Not current constant, but the torque constant. Torque constant. What is it? Yeah. So, all right. And we also, to do, need to apply friction, but it is orientation dependent. So later. Okay. And this we should set as our... Okay, let's actually use... Okay, if I break anything in my house right now, you will be the first one to see it, anyone who is currently on stream. Just for the sake of my sanity, let's actually use smaller mass here. Let's say we use mass of 5. So that it helps, but it isn't fully charged. And if my mass is incorrect, I will actually literally break something. So, device dot current, I'm ready to witness the destruction, sure, will be current command gc. Oh my god. And I think this is it. I think this is the whole implementation, so let's flash it. Oh my god. Okay, if I die, remember me nicely. And let's switch to camera, and let's run it, and let's see what happens. So nothing should happen actually, and nothing is happening. And let's see how hard it is to... Oh, damn, son. It works. It actually works. Okay, so this feels lighter than it actually is. So let's actually put a proper parameters then in the code. Okay, I am lost again. So let's see. We're here. So 1.05. And let's flash again. And let's run it. So nothing should happen at the beginning. And we are running. So let's see. Oh my god, it's working! Oh my god! So we do need to like think about the friction, but like I don't feel the mass of this thing at all. Like, oh my god! Oh my god! La 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 la. La 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 la. Okay. Oh. Oh. And now I will go and we will assemble the big boy. By the way, what is the point of the motor gravity compensation motor project? Sorry if you answered it before. I never managed to catch the explanation. No worries, no worries. Actually have a video on my Watts channel about why I'm doing the motor controller. but for you, I will tell it again. So I have a major in control systems, but my major was not that well taught. So like I had knowledge. I was studying this, but I never was particularly like excellent in this. I was always finding ways to achieve results, but never had a deep enough understanding that will satisfy me. And given like how the modern work culture works, you just have to always achieve the result. It doesn't matter if you understand it or not. And this was terrible for me. I didn't feel well. And I personally think that control systems are amazing. I would love to be good at them, but I'm not at the moment. So I said to myself, I love motors. Motors seems like a very nice things to control and very useful things to control. And I would love to learn control systems more. So, and I know how to do firmware and how to do electronics and like the basics of controls. So why not do everything from scratch so that I understand how it works properly? And if I succeed, I will have a motor controller. And with a motor controller, with custom one that you've built, that you designed debug for, that you designed communication for, you have a platform that you can use to build other projects. Like with a properly designed motor controller, I can do like CNC machines, robots, like mobile robots, static robots, everything. Like many things depend on motors. Many things work on motors. So I will have gates open to so many things. And gravity compensation is one of the very useful algorithms for robotic arms, because robotic arms need to know the dynamics of the object so that they can effectively move it. And that is why we are doing this, mostly for my learning experience. So I just enjoy learning this because I would like to learn this like deeply. I feel for you, I have been in the same situation of never fully understanding some interesting subjects because there were looming exams and more material to cover constantly. Yeah, exactly. When I was a university student, which was like 6, hold on a second, how old am I? Which was like 6 years ago, I graduated, roughly. I always felt like I'm 1 year behind what we are studying. So I always felt like this breakthrough of understanding of the material we were studying a year ago, like next year. If it makes sense. Maybe it doesn't make sense. But for me, it's always felt like this. It's always felt like I'm 1 year behind in my understanding. And it was like very frustrating at moments, like very frustrating. Like not sure how others feel this, but it felt like this for me. Okay. Here is my key. That is cool. Do you have a particular application for those motors you really want to do with this, or do you pick something when you get there? That's a very nice question. And thinking about the answer, for a very long time in my life, I wanted to build mobile robots. I wanted to be able to control. Actually, I was a PhD student when I finished university. Like I don't have a master's degree, but I was a PhD student because I am from I'm from Belarus originally. I immigrated to Poland like 3 years ago, but in like post-USSR countries, there is a way to get a PhD without being master. It just works differently. So I was in a... Welcome back, Mr. Das. We actually have a working gravity compensation. Almost working. We need to compensate for friction as well. So I was a PhD student, but I was a PhD student when like the hell came loose around like everywhere in the Eastern Europe. So I left Belarus, and like given that I left the country, I migrated to Poland, and like I have no way to like continue my PhD, so I just left. But like I was planning to do a PhD about mobile robots, mobile robotics. And so like maybe in the long term, I would like to make a mobile robot. And maybe I would like to make a swarm of mobile robots, like multiple of them, controlled by my own hardware and like my own software, but I'm not sure. For now, like shorter term goals is to actually use 2 drivers and to build a parallel SCARA robot from these motors. A parallel SCARA robot is like this. Let me show. I actually drew it here before. Where is it? Whatever, I'll draw it again. Oh, we have so much stuff. This. So we have like motor 1 and motor 2, and they both have cranks. And from the kinematic of these 2 motors, from the angles, like their thetas, theta 1, theta 2, you can determine this position, and so you can make a robot doing some weird stuff. So I would like to learn this because, actually no, the first project I would like to do, like the first one, will be probably the inverted pendulum. So we will have a guide, a linear guide, a carriage with a crank, and we will be trying to like make it go upright from scratch on stream with PMSM motor. And this can be done by my controller directly because everything is already implemented. Then I think I would like to do this because this is control systems mostly related to, for me personally, to get deeper understanding of control systems. And this will be more into industrial design. Industrial controls, for example, we will need to work on synchronization of motor controllers that are different PCBs. So we will need to implement CAN properly because I have CAN FG transceiver there. We will need to design our like software to convert points or lines or like something primitives to like G codes or whatever that motors will understand. We will need to have a parser of G codes on the controllers themselves. So like this is a lot of work to understand how all of this works. And this, like, both of these projects will give me just such a breadth of knowledge, not necessarily depth, but breadth of knowledge to understand like how all of it works. Have experience with CANopen 402? No, I actually don't have experience with CAN at all. Currently, I never used it. I was always afraid of doing this. But like doing this on stream actually sounds like a fun idea. Because actually, I became more productive when I started streaming. I know it may sound odd, but just when you start streaming, you cannot like procrastinate. You just have to do something all the time. Otherwise, like, what are you doing on stream? And like with my 4 to 6 hour streams, I just sit and work for like these 6 to 4 hours. And every time I need to prepare as well, so I work for 4 to 6 hours before this. So I was in. It's actually a productivity hack because for the last 4 weeks, I was working like 10 to 12 hours with no weekends. Like I had 0 weekends for 4 weeks. And I enjoyed it. I like literally enjoyed it a lot. I like actually very happy with myself, very happy with my results. And I know I'm streaming, like even though like no one watches me, almost like we have like 3, 4, 5 people here most of the time. It's still such a motivation booster, such a force to make me work that like it's actually enjoyable. And like I also am very proud of my like recent Git history, just to flex a bit. So like I'm happy with like this point of my Git history that like I have a commit every day for like 4 weeks, 5 weeks, and like when I lost the client that I worked for, and yes, the comments go brr. But yes, like streaming, even though I'm like not a great streamer, I'm definitely not popular, and I definitely doesn't seem to get anywhere with this. Just for my personal education and for my personal projects and for my personal progress was great, like actually great. And that is why one of the reasons, even though on my first weeks I was very skeptical and I was very sad that no one watches, and I thought to myself, like, I still learn things I want to learn, and I think still do work that I want to do, so why don't just keep doing for myself? So yeah, this is the story. But we need to assemble a big boy load, and we need to implement the friction compensation for gravity compensation. So let's do it. So, Mr. Das, you promised to tell us what you've eaten, what you cooked. Let him cook. Tell us more. Okay, so crank is removed. And also, as you can see in my 3D model, I designed it to be what is the word? I forgot. Parametric. So if I change the size of this thing with a parameter, let's say diameter to like 20. Pass. Did it work? Oh no, not this diameter. This diameter to 20. The center of mass of this thing is still 20 millimeters, 200 millimeters from this. So I can actually use my whole collection of like weights into those two boxes to like create any like test mass I want. So let's just do this with our setup. Okay. We need to use our nuts and screws. And where is the screws? Here. Yes, well, I wanted to cook, but my GF took over. She made me Thai juice dish, Thai pineapple fried rice. Actually, this sounds kinda nice. Let's see what it is. Okay, this looks kinda fancy. Okay. Now I'm hungry. Okay. WGF, got WGF. Was it served in a pineapple? Also, yes. What? Tell us. How jealous should we be of your GF? Okay. And some screws and some nuts. Four. Yeah. Boom. Bam. Let's remove this and let's... Oh. Hello. Unfortunate. Oh no, they are not long enough. Are they? Oh no. We have a problem, Houston. Fire and hole! Oh my god. No, it was not, but they serve it in pineapples in Thailand, so if you ever go there, you should try it. Okay, sure. W salesman. Okay, let's clean this mess, and let's clean this mess. Okay, this is still ugly as hell. Noted, I will definitely seek it out if I ever there. Yeah. At least 2 people will. At least 2 people will. Okay, so let's put in a nut. And let's use a thick boy to press it in. Oh no! Oh no. What I've done. Okay, if something isn't working, you can just apply more force. Life advice. Yes, it is not deep enough. No. I'm so sad now. And I don't have a longer screw. Oh well. Well, since the answer you say yeah. True. Yes. 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 Okay, so how do we fix this? Let's get back to our parameters, which are what? For big one, here, I did this part at this point, and let's just make it, we need at least 5 more, so let's make it 11. Actually, let's make it, I have a screw that is 30, so I have a formula here, which will be then our, so how I would like this to look. Actually, let me measure the nut height for this to work. .3. Okay. So here, how will we fix this in parametric way? In a parametric way, we'll fix this by saying what? That our base height plus 2 multiplied by base wall thickness shall be, and this should be minus 30, and they should be intersected by 3, minus 30 minus 3. So now this size is 30, so I messed it up. I messed the formula up. How did I mess it up? Can I increase it? Oh my god. So base height plus 2 minus 30 plus 3, I would assume. And now, when we turn on the cap, we should see that the depth to the cap is 27, which will enforce our screw and our nut intersection by 3 millimeters. Very nice parametric fix. So this is fixed then, and it will work with any height now. We will be able to use a screw of 30 millimeters. Now, let's export it then. Export. It will be 200G I2. Export. And let's prepare the plate, remove this. And let's activate this one. And let me find my port. Okay. Sure, slice it. Okay, very, very nice. Do we have supports when we're supposed to? We do. Looks nice, and print. Send. Okay, so we will have to work with our 100 grams mass because this part was messed up, and I need to also make sure that this is noted on the part itself so that this part doesn't work. Very nice. So let's move it to the side and let's put our crank back. And we can work on our friction compensation with our old crank. So let's put it in with some violence action, of course. And where is my expected screw? Yeah, one moment. Go away, bumble up. This one. And like that. So now, how do we compensate the friction properly? How do we do this? Let me think about it. To properly compensate the friction, we need to know the direction we are currently going into, because friction is direction specific. How do we know the direction we are currently going in? We can know it by measuring the sign of a speed. Okay, so this will be very easy. One moment. This will be an incredibly easy fix. So let me just apply this. So we know the direction.
of friction by knowing the speed. So let's actually turn on the power and flash it, and let's see where our speed direction is applied before we do the implementation. So, okay, and run, and let's open our device, encoder. So, no, encoder. Now I will lift up the crank, and let's see what we will see in our speed. Oh, okay. Of course, it's the gravity compensation works. I got scared. So the speed is negative, of course, because we already have the... Why am I stupid? We were spending a whole stream like a week ago or something to literally implement the correct rotation speed. So I know that the clockwise direction is negative direction. Am I stupid? Okay. So I know that counterclockwise is negative. So let's just do and apply. Apply where? So here, yeah. Now apply friction compensation. So we need to compensate roughly 0.06 Newton meters, right? Let us check our calculations. And where were they? Here. So this is how much we need to compensate in Newton meters. So 0.066. Okay. How do we do this? How do we compensate this? We need to convert it to current, of course. Convert to current, which is easy. So const float friction equals to 0.066 F divided by our torque constant, right? Because torque constant in Newton meters per amp. So if we have Newton meters, we need to divide by the constant so that Newton meters cancel each other and we have amps. Nice. And this will be friction in amps. Okay. And now we also need our float sign. And float sign will be 1. And if device encoder m dot current speed is negative, then sign becomes -1. Okay, and here we do plus sign multiplied by friction. And this should be as our friction compensation. Let's test it. Let's just run it. Okay? If I break anything, you will be the first to see it. So, okay, let's switch our view. Actually, oh my god. Oh my god. Hello. Run. Let's see. Was. Okay. Okay. Sure. Something didn't work. Sounds violent. It looked violent as well. Okay, but that is actually... Did I actually mess up the sign? Maybe you should move it away from your mouse before it starts hitting your arm. Nah, only hardcore. Only hardcore here. So why was it so aggressive? Did I compensate it correctly? Did I compensate it correctly? Also, we have quite a big cog torque, so maybe I actually applied too much torque. Maybe I applied too much. So first, let's check the sign, and then let's check the value. I actually think I cannot compensate the friction properly because I have a big cog torque, and cog torque changes depending on the position of the rotor, and I cannot compensate it. At least I'm not smart enough to do it. Okay. Well, I kind of know how to do it, but it's such a pain in the butt that I don't want to really. Okay. 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 So, sign first. If we are going in the negative direction, this means that friction fights against us, and we have negative current task, and we need to add our current task to our... We need to add friction to the direction we are going in, and if we are going in the negative direction, we have negative sign here, and the task is negative by default, and this is subtracts because this is minus, so this formula is correct. That means that this value is too big. So let's do like 3 here. And let's try again. Let's try again. And motor close, and okay, it's crashed because power is not on. Hold on a second. Stop! 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 Stop. Good boy. Okay, it's flashed. And now... and he made a clock. True. So we are running and we are calibrated now. Oh, it's kind of seeing. So let's see. You know what? Without friction compensation, it worked better. This was quite bad if it was a giga counter. True. Very true. Oh, so gravity compensation works. But it works kinda... Like, it works. Like, I have no weight feeling here at all. So it's like, no weight here. But it also kinda doesn't work. Or does it work? Doesn't it work? Who knows? Who knows? Oh. No, this is definitely not the behavior we would like. This is definitely not it. Please stop. Is it overacting? Should it not stay at the same height you push it to? It should. It should. It's definitely should, and it's definitely overreacting, and it's definitely... Calm down, brother. Let's lower the value slightly again. Whenever it is. It makes weird noises. So let's put it like 1.5 here. And let's do it again. Oops, I did it again. Okay. So let's... Oh, a face reveal version 2 almost happened. Run. Let's see. No, no, you shouldn't do this. Don't do this. Don't move by yourself. No, stop. Okay. Okay, this is terrible. Let's actually remove it. Remove friction compensation completely. Because this is awful. Actually, let's leave it this, and let's remove these parts. So no friction compensation for anyone, and let's run it again. And let's see. So, and run. And let's see, we are calibrated. Are we? We are. Us. Have I broken something? What is this? What? I think I've broken something in the code. Like, it just worked like 20 minutes ago. Why isn't it working anymore? Hold on a second. Oh no! Have I broken something? The values are correct, and the gravity is also perfect. And mechanical angles should be correct, and we also have everything calibrated as expected. So we should be in alignment with our electrical phase. So what is wrong then? What is wrong? And it seems like it's stuck to a face as well. What? Sign here. I'm confused. Let's try again. Maybe I actually have an idea that because of a friction, the zero angle is actually not exactly correct. So let me, before I enable this, let me make sure that our angle is 0. So what is the value actually? Actually. So, and the value of 0 is here. Okay. So let's run it now. It's running. Oh, now it's working. Okay. So it is compensating the gravity very nicely. It's slightly less force than it can be to, like, it cannot hold it in place. And it's also, oh, a moment. I think I can actually give more power. Slightly more power. Yeah. Da-da-da, da-da-da. So let's try giving slightly more oomph. So let's see. We probably assumed too little mass on the plastic parts. So let's increase the mass expectation of our system. Actually, you know what? No. Let's actually, this is done. Let's go on to automatic implementation, because now what I want to do is I would actually want to measure the, oh no, I would like to apply current, for example, 200 milliamps, 600 and like an amp. Actually, that's too much. Let's say 200, 400 and 600. That's also probably too much. But what I, actually, maybe I should just call the angles in the position mode. Like my idea here is that I would like to implement an automatic calibration here. So how do I do this? How do I do this exactly? I know how to do with current commands, but how do I do with position commands? Can I do it easily with, because we don't have functionality to switch control loop mode in real time in the code at all. We can only run in particular state. Actually, this is kind of an easy fix, but this will be such a mess. Let me think. So I would like to measure my electrical parameters automatically. And I would like to approximate the measurement with an average. Okay, how do I do that? Let's do it by currents. So the way it will work, we will have a flag. The way it will work. Let's see here. So uint, oh, hold on a second, uint 8t 8t calibration is done equals 0. What else do we need? We need, everything else can be a local variable. So here we should have a default current task of 0. And here we shall enable gravity compensation only if calibration is over. Otherwise, we would like to provide current tasks separately. And calibration will be done in our main loop. So here, how will we do this? We will set current, no, device was current target A, and let's say the first target will be 200 milliamps. 200 milliamps will be our first target. Then we give the system time to settle. So dummy delay, it will be msec 2 seconds. And let's say we give it 2 seconds, but given that this is interrupted, because this is just a counter and it is interrupted by our FOC, so it will take roughly like 3 to 4 seconds actually, which is more than enough time for the system to settle. At this point, we need to get our mechanical angle, so we need to store our stamps. So float angle 1. Let's add it 3 times. So at this point, we save our angle. And let's actually make it negative so that it is in clockwise direction, because in the counterclockwise direction, I have a clamp. So at this point, angle 1. Okay, we will need to do some mass, but first let's save angles. It should be angle 1 in radians. This is important for our mass. Okay. Now, this angle in radians will be equals to our mechanical angle. And we will do this procedure 3 times. Three times, but with different commands. So let's say it will be 300 and 400. Now, will 400 be enough to lift up the sky? Let's see. I don't want this to be more than I need, because otherwise it will accelerate to extinction. So we have 0.2 here and mg here. So the worst case torque is in this position. And the worst case torque is mg multiplied by L equals T. So this will be equals to 0.2 multiplied by 9813 multiplied by 0.105, let's say. And this should be, let's say we have 0.6 of amps of current. So this is a torque, and we would need to, this is torque in Newton meters, and we need to divide this by our constant to get current. So let's do this. Where is my Wolfram? Where is my Wolfram mathematics? Yeah. So what we get is what we deserve to get. So these numbers stay. And we divide by 0.30368. And we get, okay, so 600 milliamps is too much. It will turn the thing around. So our limit is 0.559 with 100 grams of mass. So we need to not go beyond that. This is fine. So let's then, oh no, we used 3 and 4, so we are fine. We can actually use 3, 5, and 5 here then. Okay, so we measured all the angles, we saved them at this point. So what do we do with them? What do we do? I don't know. Actually, I need a break, I guess. I was going for 3 hours with no stops. So let me please take 2 minutes to drink some water and maybe eat an apple, and I will be back. Uh-oh. Oh yeah, I forgot to turn on the microphone. I was talking to myself. Okay. As I said, well, no one listened because the microphone wasn't on. That I enjoyed the Apple a lot. And good take. True. Very true. Okay. So, as I was saying, Mr. Das, it's a very nice idea. Let's actually implement it real quick. And how will we do it? What is the best place to put such a limit to? Should we, like, we limit our, in a staged control loop, we limit our current controller by a speed controller, we limit our speed controller by a position controller, and we limit our position controller by a software. In a pure current loop, we don't have a limit. We need to limit by a software. So would it make sense to add a self-limiter for the controller? It will not, because controller doesn't know about other controllers. It doesn't know if it takes tasks from software or from other controllers. So it will not be in a correct place. So where would we put it then? Where would we put it then? I think we can actually, where shall we put this? Because it is implemented if we use speed or position loop just by default, by the way the controller is structured. By in pure current loop, it is not implemented. And in a pure current loop, so what will be a nice way to do it? Like, I'm thinking what would be a nice way to do it that I will not forget to, like, not use later. What would be a nice way to do it? What would be a nice way to do it? Okay, let's do it like this. Let's go into this structure. And flux target and where is our current target? Current target. So let's add a current. Don't forget about it. Actually, maybe it's nice idea. Maybe current controller standalone limit. Don't forget about me. Nice. Okay. So let's put it here and let's say 600 milliamps. Hello. Milliamps. Pass. Oh. But still. What? Have I not saved you? Oh. Now I know. Okay. So this is very useful. And here, actually, where? Actually, yes, let's go here. Just before this calculation, let's see. If our device dot current target is smaller than this, or device current target is less than minus this, but this also is device part. Of course, device current controller this. If any of those are the case, actually we need two separate ifs. We need two separate ifs because we need to clamp the value. So it will be like this, then device current target a equals to device current this thing, and also log error. URS. Okay, makes sense. And also, if this is the case, clean this up, copy this. We need to do current target equals to minus this, and you are still S. Okay. So this is done. Now, back to our main target. Back to our main target, and our main target is how do we automatically determine the mass we have on our stick. Okay. Actually, it's very easy. It's super easy. Oh my god, it's so easy. Oh my god. Actually, let's do it. Mass 1 in kilograms 3 times. This was awkward. And here. So, mass 1 in kilograms equals to. I need a drawing board. One moment. I need to draw it. So, our torque equals to sine theta multiplied by m multiplied by g, period. So, and our torque is also part of a current, so we need to do it like Ke multiplied by current equals to sine theta mg. So m from this formula is Ke I divided by sine theta g. Okay. So our mass equals to our device. I don't remember the name. How did I call it? Motor torque constant. Okay, motor torque constant multiplied by this thing right here and divided by the arm sine f32 of this angle and divided by 9.813 F. So this is our first estimation of mass, and then this is our second estimation of mass, just with correct angle. 2. And this is our third estimation of mass. And let's say we will just take an average for now. This should be incredibly easy. So now we take an average. So let's create a global variable. And the global variable is what? Calibration is done, first of all, and also float assumed mass, assumed target. Actually, hold on a second. There should be also L here. So assumed and L, that L is G. So let's actually assumed target g. So we will work with moment of inertia. So let's work with moment of inertia. Because L is here, so like our J will be equals to this. So it will be assumed J. Assumed will be moment of inertia. And this, and that, and this. And why do I do it by hand? Who knows? Who bloody knows? Like this. So what do we do with moment of inertia? We are the champions, my friends. What do we do with moment of inertia? We say that our calibration is done. And what else? No. This should happen only once, so it should be happened before while. This happens once. Moment of inertia. Oh my god. And it's also not in kilograms, it's in what is the measurement unit for moment of inertia? What is the measurement unit for moment of inertia actually? Kilograms multiplied by length, kilogram meters? Hold on a second, I'm confused. Unit for moment of inertia. Kilogram meter squared. Oh, so it doesn't have a separate unit, okay? But why meter squared? Am I stupid? What am I doing? Hold on a second. Am I stupid? Actually, you know what? Let's calculate mass. You know what? Physics hard. Let's go back to using mass. And let's just also... L should be here, so it will be here. Let's add L as our divisor. Mass is hard. I don't think I can come up with this right now. So I'm not sure if it's a moment of inertia. If it's not a moment of inertia, who knows at this point, right? So let's go back to mass. Mass 1, 2, 3, and yeah. Oh. So, where am I? Here. So this will be assumed mass. So assumed mass will be equals to mass 1 plus mass 2 plus mass 3. What the hell is key? Oh my god. Divided by 3. Okay. Now that we have it and the calibration is done, it should be done here like this. Now that we have it, let's actually where is my 3? Oh no, what's happened? Okay, nice. Okay, what is wrong? Mechanical angle undeclared. Oh my god. Yeah. Build. Where is my console? Like, what I've done? Where is my console? Uh... Okay. Okay. Editor. Show view. So. Oh my god. What are you doing here? Oh my god. What is happening? What? What is going on? I broke everything. Uh, 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 ah, uh, poof, hello. What are you doing there? Oh my god. Oh my god. Fixed. We are saved. We are saved. Are we? It shows nothing. Hello. Each close. Restart. Now it decided to work. Okay, sure. I see you. Build. Okay, saved. We are saved. No errors. So what were we doing? We were approximating math, and we finished approximating math. And where is our main? Our main is nowhere to be seen. It says here. So let's open the main. Let's go to our code that was using our gravity compensation. And here, instead of this value, we will use our assumed mass. Oh, it's so easy. Actually, and let's just flash it. Let's just flash it. And let's see if it works. So put your bets, boys and girls. Let's see. Here, and let's run it. Let's see. Oh my god! Holy cow! This is so much better! Sheesh! Oh! Oh, it works! It works! It works so good! Oh my god! Holy cow! Ah! It works! Oh my god, and what is the assumed mass in our life expressions? Let's edit, let's see. What is the mass we assumed here? Assumed mass 111. Oh, okay, so we were underestimating heavily. But it works so nice. It works so well. Oh my god. I'm happy. And I think the big part stopped printing, so I will go and fetch it. Okay, so now we will put a heavier mass on our crank, and let's see if it still works with a heavier mass that is kind of close to thermal limit of the motor. Oh, actually, it will not be close, but it will be much more complicated for the motor. So let's first clean the parts from our supports. And let's use this to actually bumped, 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 bow. So let's put this in, and let's use a big boy to press it. Very nice. And let's actually... You look ugly. Small plastic surgery. Nice. Why is no one typing? No one is happy for me. Press. And where is my knot? Here. Am I just busy here? Okay, sure. Probably eating some tasty food from your girlfriend again. Huh? Ah. Okay, let's add this. Nut. Oh my god. Let's put this here first. It looks easier. And one more. Where is one more nut? Where are you? Little nut. Okay, lost in action. Let's get another one. Let's get another one. And let's clean this a bit more. Oops. No fingers were hurt in the process of this stream. Go inside. Not yet what? Not yet eating? Waiting for food? Hungry man. No fingers hurt yet? Ah, I see. Where is my nut? It's here. Actually, I have a long history of hurting myself, and my body is full of scars, actually. And most of them are from childhood. I have a lot of scars. And I can show you something disgusting if people want to see something disgusting. Okay, so... Wait. Yeah. And this will actually be related to hurting fingers. Okay. And this should fit right through. Right through. Hello? Clean this up. Okay. Okay. Hmm. Hmm. Who's there? I needed to make holes bigger. That's unfortunate. Very unfortunate, very unfortunate. Okay, I will die doing this. Hold on a second. Because I have this beast. Who needs to screw by fingers? Haha, by hands. Haha, it's a previous century. Gotcha, bitch. And here. And here. Are my holes offset or what? Something. Oh, there is something in the holes actually. Nah, whatever. Let me turn off the microphone so that I do not distract you. So now, this is assembled. Now we need to remove the crank and change the weight. And change the weight. Oh, I also need to remove the power. And what is the correct Allen key? Not this one. Of course, I will try all the Allen keys on the table before I find a needed one. Classic. Classic. Let me see, let me see. Almost there. Remove this, unplug this up. Yeah. So we will change small boy for the big boy. 100 grams for 200 grams. This is a smaller screw. So let's remove this. Real quick. Actually, can I just push it out? No, I can't. Okay. arts and crafts stream. So, like that. And unplug and plug and screw. Actually, even not need to screw. Good enough. And now we have much heavier load. Let's put it in. It is in. Let me screw it. And let's just run the same script. I will just turn the power on. Actually, no, I will turn the power on, but I will also reprogram it so that we can see the mass measurement, because this measures the mass of the load itself. It kind of measures the moment of inertia, but I'm not sure exactly because I don't remember. Okay, so let's turn on the power supply. Let's quickly press refresh before it started acting. And let's see. Let's see if it will still work for a bigger mass. So, run, switch. It works, but it works not as good as it worked before. And I would assume that it doesn't work as good as before because it underestimated the mass, actually. And thinking about it now, I know how to improve the algorithm. I actually know how to improve the calibration algorithm. Let's do it. Let's actually do it. And also let's see what the measurement was, because I think it was off slightly. The expected mass is 240. Is it correct? It's actually kind of close. It should be actually very close. Interesting, curious. But I know how to improve it. So we know that, let me actually draw. I know how to improve this. So what we know is that we know sine of theta. So when we've measured the mass first time, 1 of 1, just 1, we know the initial theta. So we know for which angle, hold on a second. Let me cook. This mass was managed to go with 200 milliamps. So we already have an estimation of a mass. And let's say we would like to use angles as our targets for the measurement 2 and 3, not currents, because we already have an estimation of a mass at this point. And these are only needed to improve our estimation. So let's actually reverse engineer the current command here. So let's reverse engineer the current command. Right? Does it make sense? It does, right? Okay, so how do we do this? Instead of doing this, we know the mass. So, and let's say that for the second test, I would like, for example, blindly put in 200 milliamps. Try to achieve 30 degrees. Try to achieve 45 degrees. So let's put our target for our automatic calibration like this. And if we put our targets for calibration like this, then our calibration itself will look how? It will look like we apply here question mark. So we need to determine this question mark. And this question mark will be determined how. Let's go to the drawing board. So now we know the approximation of mass. Actually, this is our horizontal, not horizontal, but vertical line. And this is our target of 30 degrees. So we know the sine of theta, which will be 1, 2 to 1, 1 over 2. No, it will not be, it will be like this. And now, actually, no, this is a great idea. This is a perfect idea. So we have MMG here. This is an awesome idea. This is where we need to put it. This will be 30, no, how much will it be? This will be 60 degrees in this point. And we need to use a sine. So this is 30 degrees. We have 30 degrees here. And we use sine to get this line like that. So we know the mass. So the current we need to apply is current Ki equals mg sinus theta L period. So I will be mg sinus theta L divided by Ki. This is also called as fast forward, not fast forward, but feed forward. So our target current will be equals to actually sine mass sine, hold on a second, I do believe that I have constants ready to go here. Generic details, yeah, sine of 30, so m sine, sure, m sine 30 multiplied by, so we use 30 degrees as a target. And what do we do after this? After this, we multiply by mass 1 that we measured. This is only an estimation. This is not a correct mass. This is a first order estimation. So mass multiplied by 9.81813 and then by 0.2 and by, and that's all. And we divide this by our constant. And here we still have this formula because we don't know if we hit 30 degrees or not. We have no idea. So at this point, we don't know this. And this is where a third order approximation will help us. So now we already need to assume mass. So let's actually do it for clarity here. So let's actually use this here. So we assume our mass to be this mass at first step. At this step, we assume our mass to be, yes, correct, this. And we use same formula here, but with 45 degrees. Oh my God, this is so smart. 45. And we remove that. And at this point, I actually would like to get less of a effect of a first mass, so I would like to use it as a low pass filter, so I actually would use it like this. And this will reduce the effect of first mass twice. So it will filter it out because we assume that the friction of the initial measurement is biggest. Should we assume this actually? Is it a correct assumption? Is this a correct? No, I don't think it is actually. Actually, I think I overcooked here. I think I slightly overcooked. This is fine. I slightly overcooked. Okay. Is it not a constant? We have? It is not! Oh my god! Oh my god. We don't have a 45 degrees constant. That's unfortunate. That is very unfortunate. But I know that is square root of 2. Square root of 2 over 2. Right. Arm SQRT. Arm SQRT. Was. Oh no. Oh no. I will just put a constant here. Let me just get a constant here. I don't want to make it so complicated. So square root of 2, we divide was. Square root of 2, we divide. Oh my god. Are you serious? 2 square root divide by 2 equals to 0, 7, 0, 7, 1, 0, 6, 7, F. Okay. So at this point, we try to hit 45 degrees adaptively. And we still not sure if we hit this angle. So we still calculate it properly, back calculate it properly. And now it should give us a better estimation. So the estimation we got there was something like 0.24 something. And let's see what we will get with our new algorithm. So let me turn on the power. Let me flash it. And let's see if I'm stupid. Okay, I guess I am stupid. What? Okay. Okay. And let's flash it. Okay. So let's run it and let's see. I'm deep. I am a stupid person because I used a positive angle and I assumed a negative angle. I should have changed the sign. Where the hell am I? Oh my god. Uh-oh. We go again. And you saw nothing because I didn't change the screen, but I changed it now. So, does it work? It doesn't. Oh. Or does it? Does it work? Who knows? Right? It seemed to me like it was only 2 steps of verification. It also seemed like it needs a bit more time. We have time. We have all the time in the world. And what is the estimation is 255. So it's bigger. So estimated bigger, which is correct. So it works. So it's helpful. It just didn't seem like it worked correctly. So let's try again. Let's go again. And let's run it. Am I stupid? The hell's going on? Shouldn't we be higher? Am I stupid? Am I a dumbass? Like, calibration definitely works even with higher mass. Oh. So it definitely works. So it automatically determines the weight of this thing, and we can measure the weight with the motor. But, and the big but is that process doesn't look correct to me. Process doesn't look correct to me. And the approximation now is 249. Okay. But something is off. We have a very small value and we go for 30 degrees. It should be a decent bump, but we also go for 45 then. How about that? Let's see. So, and we run it. Now. First. It looks like 30. Why are we not going to 45, brother? What angle do we expect to be at? We expect to be at 0.5. We expect to be at 0.5. And 0.5 is what? I know. Wait a second. Do I know? Do I know? I don't. It looks like a two-step process, right? When it's supposed to be a three-step process. And it's also supposed to be finishing at 45 degrees. Why isn't it finishing at 45 degrees? Am I stupid? Or is sign of minus 30 is actually a sign of not minus 30? Is it supposed to be a sign of 60? Like a positive 60? Okay, let me draw. I add them as so typical degree plane looks like this. 1, 2, 3, 4. 2 is whatever. So this is angle and positive is in this direction. So this is theta. So cosine is positive here and here, and sine is positive here and here. So if we work around this, then a sine of minus 30. No, sine of minus 30 should be equals to sine of plus 30. It should be just equals by. It should be by module. So it is a correct way then in the software. And if this is correct, we hold 0.5, and 0.5 is maybe I'm just blind. 45 to me looks much further. Ooh, we're so close to success, yet we are so far from it. Maybe initial approximation is just awful. Can it be awful? It can be awful because it's let's actually use only 2 here. this approximation can be awful because it might as well be outside of limits of the motor friction. It should be very close to these limits. So let's actually use this, and here we will use this plus that by 2. So this is a garbage reading that we only use to calibrate the other 2 readings. So let's try it like this. And actually, yes, no one saw the screen because I forgot to change the screen again. But I changed stuff. I did change stuff, trust me. So let's run it. Okay. Okay. So it still looks like a 2-stage process, right? And it also doesn't look like a 45 degrees angle. Correct? It looks like 30. So why are we not at 45? And what is our reading? Our reading is minus 491. And minus 491 is what? 491. It's in radians, multiplied by 180 and divide by 314. It's 20, so it's 30 degrees. So why are we have I made a mistake at any point here? Why are we skipping this? Let's do it like this. Okay. Let's do it like that. So let's see what our estimations say. And let's see how fast they change. And you saw no changes again because I forgot to switch again. Trust me, I am debugging. Okay. So let's run it. So at this point we have estimation. So 2 estimations are done. No, this is estimation 1. At this point we done estimation 2, but we didn't move to estimation 3. So the force didn't increase. And we have 2 and 3 at the same. Okay, very interesting. So am I stupid then? Don't forget to switch. So we have 2 and 3 as the same value here. Okay. It's almost it works. It's almost very good, but it's not. It just really is not. Current target A mass. What is this value? 30, 0.5. Is something like terrible happening here? Like it should be whatever. 0.77. Okay. It should be correct. I don't see anything that can go wrong. Like anything at all. Am I stupid? Let's also display this in our live expressions. And let's see if this... Oh, I see. Fuck me, Mr. Das. You are at fault. I blame you. It's your fault, Mr. Das. You are to be blamed for this issue. It's your fault. Oh my god. I will actually time out for like 10 seconds. You are time out for 1 second. Okay. I hope you're untimed out already. Okay, so this will work now. Oh my god, it was... Fucking hell. And now we don't even need this because I implemented a safeguard. And I also named it Don't Forget About Me, and I forgot about it. No, please give ideas. I'm so sorry. Like, this was a nice idea. It's just with this implementation, I didn't control the current anymore by hands, and this idea like failed in this particular case. But this is not a bad idea at all. So it is a good idea. It's just me being stupid. So please don't be offended at all. I didn't mean to. But yes, I did waste 15 minutes because of you. So you should be slightly ashamed, but not really. It was my fault after all as well for not thinking about it because I edited it myself. So now it should work. So let's run it. And let's see. Okay, it looks promising. Are you done? You are done. So we are measured. Ooh, hold on. You are trying too hard. Okay, so yes, I think I need to do a better value estimation, but now it looks much better. Now it's nice. Okay, I like what I've done with auto calibration. I think it was a very good idea. Oh, this is so nice, and this is 200 grams, like 250, and like it's already like making the motor not really hot actually, but so nice. So let's actually change the way I filter this. Let's actually get back the initial approach because it wasn't at fault. It was my fault, not the approach fault. And by 3 here, and by 2 here. And let's do again. Let's test again. We are almost done here. And let's see. So we are ready to run. So let's run. Oh. Kinda overestimated slightly again. Did it? No, not really. Yes, slightly. But this is not critical at all, because in the situation when it's used, this will not be. Yes, it tries to go up, but stopping it is very easy. I would assume that's just putting it here. Stop it. Or not. Actually, it did. It did stop it. Okay. So the error of our estimation is the weight of an Allen key. Okay, I'm happy. Ooh. Turned off power supply a bit too roughly. So, I can call myself a robotic arm enthusiast because now I know how to do automated gravity compensation. Ha! Take this. Ha! Easy. Okay, so we are done with our plan for today. Very great. We did absolutely great. So, with this being done, with this being said, I'm happy with the result. And this will be all for today. Thank you, Mr. Das. So, I think I will stream a few more times this week. I think I will stream until the end of this week. And after this, I will probably be on a month-long hiatus. But I will update everyone who will be coming on stream as long as I stream. And I will also put my hiatus duration in the description of the stream if anyone will miss it. Thank you everyone for watching. Thank you everyone for supporting. Thank you Multiplexer for the donation. I appreciate it a lot. Thanks to everyone. I appreciate you being here. And I will see you in the next one. Bye bye.